Once again, welcome to the class. In this video, we'll solve some problems on continuity from the textbook. So let's begin. Question number 1. fx is equal to 5x minus 3 is continuous at x is equal to 0, at x equal to minus 3, and at x is equal to 5. As we know that fx equal to 5x minus 3 is a polynomial function, and polynomial functions are continuous everywhere. But we have to check it at x equal to 0, x equal to minus 3, and at x equal to 5. So we'll check the continuity at x equal to 0 first. First we'll find the limit. Limit x tends to 0, fx, limit x tends to 0, 5x minus 3. As this limit is defined on both the sides of 0, so we can directly put the value of x as 0. We'll get 5 into 0 minus 3 is equal to 0 minus 3 equal to minus 3. And the value of the function, f0 is equal to 5 into 0 minus 3. We'll substitute this value in the given function. 0 minus 3 is equal to minus 3. Now, both the limit, left limit, right limit, and the value of the function are equal. It means that this function is continuous at x equal to 0. Similarly, we can check at x equal to minus 3 and x equal to 5. Now we'll solve question number 2. Question 2 is examine the continuity of the function fx is equal to 2x square minus 1 at x is equal to 3. This function is also a polynomial function, and we know that polynomials are always continuous, but we have to check it as per the problem. So first we'll find the limit. Limit x tends to 3, fx is equal to limit x tends to 3, 2x square minus 1. As this limit is defined on both the sides, so we can directly substitute the value. 2 into 3 square minus 1, 2 into 9 minus 1, 18 minus 1 is equal to 17. And value of the function at this point, f3, 2 into 3 square minus 1, 2 into 9 minus 1, 18 minus 1 is equal to 7. Both the value of the function and the limit at that point are equal, hence this function is, this implies f is continuous at x is equal to 3. Similarly, question number 3. In question number 3, we have to examine the continuity of the function. Functions are given. A, fx is equal to x minus 5. Now, as this is a polynomial function and polynomial functions are continuous, so obviously this is continuous, but we have to check it. So let C be any arbitrary real number. Now we'll check this. Now we'll check the continuity of this function at x equal to c. So at that point we'll find the limit on both the sides and the value of the function at x equal to c. So let us first find the limit. Limit x tends to c, fx equal to limit x tends to c, where c is an arbitrary real number, x minus 5. As polynomials are always defined, so no need to check the left limit and right limit separately. So this value will be c minus 5. This is the limit. Now find the value of the function at c. So fc will be equal to c minus 5. Now limit of the function at x equal to c and value of the function at x equal to c both are equal. It means that at x equal to c, where c is at any arbitrary c, f is continuous. This implies f is continuous everywhere. Because c is arbitrary, it can move anywhere in the real domain. So this function will be continuous everywhere. Similarly, we can do the part B, part C, and part D. Now let us see a piecewise function. Question number 5 is the function f defined by fx is equal to x if x is less than or equal to 1, is equal to 5 if x is greater than 1. So this function is continuous in its partitions, that is first part minus infinity to 1 and 1 to plus infinity. In both the partitions, the function is continuous because this is a polynomial function. This is also a polynomial function. So we'll check the continuity of this function at the joining of the two domain, that is x is equal to 1. Let us find the limit at x is equal to 1. Now the definition of the function is different on left side as well as right side of the function. So we'll find the left limit first. X tends to 1 minus means we are approaching 1 from the left side. Fx will be equal to, we'll use this definition when x is slightly less than 1. So it is equal to limit x tends to 1 minus x. This value will be equal to 1. This is the left hand limit. Now we'll find right hand limit. Limit x tends to 1 plus, it means that we are approaching 1 from the right side. In this case, we'll use this definition. Fx limit x tends to 1 plus this value of 5. Now LHL is not equal to RHL in this case. This is plus 1. Left limit is plus 1 and right limit is plus 5. Both are different. So it means that at this point the limit is not defined. It means that this function is fx is not continuous at x is equal to 1. Now this function will be continuous at x is equal to 0. F is continuous at x is equal to 0 and at x is equal to 2, because when x is equal to 0, the first definition of the function will be applied. This definition will be applied, which is x, and x is polynomial function and it is continuous. At x equal to 2, this definition will be applied. This is also a polynomial. So at x equal to 2, the function will be continuous. So at x equal to 0 and x equal to 2, the function will be continuous. The graph of the function will be like this. at x equal to, when x is less than 1, fx equal to x. The graph of the function will be like this. When x is less than 1 means this side, fx equal to x. This way, less than or equal to 1, so 1 point will be included. And when x is greater than 1, it is equal to 5. Like this. When x is greater than 1, this will be the graph. When x is less than 1, this will be the graph. When x is less than or equal to 1. So this function will be discontinuous. But when x is 0, at this point the function is continuous. When x is 2, somewhere here, the function is also continuous. Similarly, we can do question number 14. See, what is question number 14? Question number 14 is fx is equal to 3 if x is less than or equal to 1, greater than or equal to 0, is equal to 4 if x is less than 3, greater than 1, equal to 5 if x is less than or equal to 10, greater than and equal to 3. We'll check the continuity of this function only at x equal to 1 and x equal to 3. In other parts, the function will be continuous. When x is between 0 and 1, fx is 3, both point included, 0 and 1. When x is between 1 and 3, fx is 4, both point excluded, 1, 2. This will be the graph of the function in this region. When x is between 3 and 10, both 3 and 10 are included, that is the open interval. fx is 5. fx is 5. This will be the graph of the function. We need not to check the continuity of the function from 0 to 1, or from 1 to 3, or from 3 to 10, as in these regions the function is continuous, obviously. Why? Because these are the polynomial 3, 5, 3, 4, 5 are constant polynomials. So here in this region, and this region, and this region, the function is continuous. At these points, we need not to check the continuity. We'll only check the continuity of the function at x equal to 1 and at x equal to 3. If the function is continuous at these points, then function will be continuous in its domain. So we'll check the continuity only at the meeting point of the partitions of the domain. In this case, it is x equal to 1 and x equal to 3. Similarly, we can do question number 15, 16 and the remaining one. Now let us solve one more question. Question number 26. Find the value of k so that the function fx is continuous at the integrated point in exercise 26 to 29. We'll solve 26 only. Fx is equal to k times cos x divided by pi minus 2x if x is not equal to pi by 2. Fx is equal to 3 if x is equal to pi by 2. Now we have to find the value of k. In this problem, we have given that the function is continued at x is equal to pi by 2. It means that at this point, limit of the function and the value of the function should be equal. So let us first find the limit. Limit x tends to pi by 2, k cos x divided by pi minus 2x. Let us introduce one more variable, y is equal to pi minus 2x. So when x tends to pi by 2, y tend to 0 obviously. When x tend to pi by 2, y tend to 0. And from this we can conclude x is equal to pi by 2 minus y by 2. So rewriting the expression, we'll get limit y tend to 0, k into cos x. The value of x is pi by 2 minus y by 2 divided by y. Limit y tends to 0, k times cos pi by 2 minus theta is sin theta. Sin y by 2 divided by y. Further simplifying, we'll get limit y tends to 0 or y by 2 tends to 0. If y tends to 0, y by 2 will also tend to 0. K by 2 into sin y by 2 divided by y by 2. So this expression will become 1 when y by 2 tend to 0. So the value is k by 2. So limit of the function at this point is k by 2. Now let us find what is the value. Value is given fx f pi by 2 is given 3. This is given in the problem. Fx is equal to 3 if x is pi by 2. So since f is continuous at x is equal to pi by 2, it is given. So at this point, the limit of the function and the value of the function both should be equal. Limit is k by 2. So k by 2 should be equal to 3. It implies k is equal to 6. This is the answer. Let us solve one more question. Question number 32. 32, where we'll use the theorem number 2. Question number 32 is, show that the function defined by fx is equal to modulus of cos x. Here we'll apply theorem 2. Theorem 2 says, suppose f and g are real valued functions such that f of g is defined at c. If g is continuous at c and f is continuous at gc, then f of g is continuous at c. In this case, let us assume gx is equal to cos x and fx is equal to modulus of x. Now we know that sin x and cos x are always continuous. If you remember, you have learned in class 11th, the graph of the cos function is like this. And it does not have any break. And the graph of modulus function is like this. This also does not have any gap. We know that at every point, cos x and modulus x are continuous. So now, at every point, this is continuous. And at that point or any point, modulus function is also continuous. So it means that applying theorem number 2, we can conclude that the function, that is modulus of cos x, is continuous. Similarly, in question number 34, we can apply the theorem number 1, that is, if f is continuous, then f plus g is continuous. Similarly, we can solve question number 31 and 33. And in question number 34, we can apply theorem number 1, which says that if f and g are two continuous functions, then f plus g is continuous. F minus g, in this case, question number 34, f minus g is continuous. F into g is continuous. F divided g is also continuous, provided that g is not equal to 0. So this much only in this lesson. In our next lesson, we'll learn about differentiability. Until then, keep learning. Thank you.